What specific problem does the proposed method aim to solve in the domain of reasoning for large language models?
The proposed method aims to address the limitations of existing reinforcement learning (RL) approaches for large language models (LLMs) that primarily focus on mathematical reasoning, which restricts their generalizability to other complex domains. Specifically, it tackles two main challenges: the lack of high-quality, diverse reasoning datasets that offer reliably verifiable answers across multiple disciplines, and the inadequacy of traditional rule-based verifiers that struggle with the varied answer types found in broader reasoning tasks. To overcome these issues, the method introduces a large-scale, diverse domain dataset, WebInstruct verified, and a compact generative model-based verifier, general verifier, that enhances the flexibility and scalability of RL training. This approach enables the training of general reasoner models in a zero RL setting, significantly improving reasoning capabilities across various domains while maintaining performance in mathematical tasks. Ultimately, the method broadens the applicability and robustness of RL-based reasoning models beyond the confines of mathematical and coding tasks.
How does the proposed method, General Reasoner, work? Illustrate step by step, including how it utilizes the all-domain reasoning dataset and the general verifier for RL training.
The proposed method, General Reasoner, operates through a systematic approach that leverages the all-domain reasoning dataset and the general verifier for reinforcement learning (RL) training. First, it constructs a large-scale dataset of approximately 230K high-quality reasoning questions spanning diverse domains, which are verified for reliability using the WebInstruct framework. Next, the model employs a compact generative verifier, the general verifier, specifically trained to assess short answers in a context-aware manner, providing robust reward signals for the RL training process. In the zero RL setting, General Reasoner directly applies reinforcement learning to base models, such as those from the Quen family, without prior supervised fine-tuning, allowing for efficient collection of verifiable question-answer pairs. Finally, through extensive evaluations across various reasoning benchmarks, the model demonstrates significant performance improvements, validating the effectiveness of its training paradigm that combines diverse reasoning data with a generative verification approach.
Can you provide a simple yet illustrative example that walks through the main steps of how General Reasoner processes a question and generates an answer?
The General Reasoner processes a question through a series of structured steps. First, it utilizes the all-domain reasoning dataset, which contains approximately 230K high-quality reasoning questions across various disciplines, to select a question. Once a question is chosen, the model generates potential answers, which are then verified using the general verifier, a compact generative model trained to assess answers in a context-aware manner. If the generated answer passes verification, it receives a reward score, which is calculated based on its correctness and length, guiding the model's learning process. Finally, the model iteratively refines its responses through reinforcement learning, enhancing its reasoning capabilities across diverse domains while maintaining performance in mathematical reasoning.
What are the measurable benefits of using General Reasoner over existing reinforcement learning frameworks in terms of performance and generalizability?
The measurable benefits of using General Reasoner over existing reinforcement learning frameworks include significant performance improvements across various reasoning benchmarks. For instance, General Reasoner achieves a 10% boost on general benchmarks like MMLU Pro and Super GPQA compared to previous models, while also slightly outperforming math-focused frameworks like Simple RL on mathematical benchmarks. Additionally, the model demonstrates enhanced generalizability, as evidenced by its ability to maintain or improve performance across diverse domains, achieving 58.9% on MMLU Pro with the Quen 2, 5-7B base model, compared to lower scores when trained solely on math tasks. Furthermore, the use of a compact generative verifier allows for more effective training, leading to higher accuracy and better handling of diverse answer formats, which traditional rule-based verifiers struggle with. Overall, General Reasoner not only excels in specific tasks, but also broadens the applicability of reasoning capabilities across multiple disciplines.
What validation methods were used to test the effectiveness of the General Reasoner, and what benchmarks were focused on to evaluate its reasoning capabilities?
To validate the effectiveness of the General Reasoner, comprehensive evaluations were conducted across 12 challenging reasoning benchmarks, which included both general reasoning tasks and standard mathematical reasoning benchmarks. The specific benchmarks focused on for general reasoning capabilities were MMLU Pro, GPQA, Super GPQA, Theorem QA, and BBEH, while the mathematical reasoning benchmarks included Math 500, GSM 8K, and Olympiad. The evaluations demonstrated that General Reasoner typically boosted performance on general benchmarks like MMLU Pro and Super GPQA by approximately 10%. Additionally, the model was compared against various baselines, including Qwen 2, 5 and Qwen 3 families Simple RL and Nemotron CrossThink, to assess its performance improvements. The results indicated that General Reasoner consistently outperformed both base and supervised fine-tuned models across these benchmarks, showcasing its enhanced reasoning capabilities.
What limitations does General Reasoner face, especially regarding its applicability across diverse reasoning tasks, and how might these limitations impact future research?
General Reasoner faces limitations primarily related to its reliance on the zero reinforcement learning (RL) approach, which, while efficient, may not fully capture the complexities of reasoning tasks across diverse domains. The model's performance is still somewhat dependent on the quality and diversity of the training data. For instance, while it excels in general reasoning benchmarks, it may not achieve the same level of performance in highly specialized or nuanced fields that require deep domain knowledge. Additionally, the model-based verifier, although superior to traditional rule-based methods, may still struggle with certain answer formats, particularly in unstructured responses, which could lead to inaccuracies in verification and, consequently, in training outcomes. These limitations suggest that future research should focus on enhancing the model's adaptability to various reasoning tasks and improving the robustness of the verification process to ensure reliable performance across all domains. Furthermore, addressing these challenges could lead to more comprehensive datasets and verification methods that better support the generalization of reasoning capabilities in LLMs.